Polonium is a chemical element with symbol Po and atomic number 84, discovered in 1898 by Marie Curie and Pierre Curie. A rare and highly radioactive element with no stable isotopes, polonium is chemically similar to bismuth and tellurium, and it occurs in uranium ores. Applications of polonium are few. They include heaters in space probes, anti-static devices, and sources of neutrons and alpha particles. Because of its position in the periodic table, polonium is sometimes classified as a metalloid. Other sources say that on the basis of its properties and behavior, it is unambiguously a metal. Characteristics. Isotopes. Polonium has 33 known isotopes, all of which are radioactive. They have atomic masses that range from 188 to 220 U. 210 Po is the most widely available. The longer-lived 209 Po and 208 Po can be made through the alpha, proton, or deuteron bombardment of lead or bismuth in a cyclotron. 210 Po is an alpha emitter that has a half-life of 138.4 days. It decays directly to its stable daughter isotope, 206 petabits. A milligram of 210 Po emits about as many alpha particles per second as 5 grams of 226 Rath. A few curies of 210 Po emit a blue glow which is caused by excitation of surrounding air. About 1 in 100,000 alpha emissions causes an excitation in the nucleus which then results in the emission of a gamma ray with a maximum energy of 803 keV. Solid-state form polonium is a radioactive element that exists in two metallic allotropes. The alpha form is the only known example of a simple cubic crystal structure in a single atom basis, with an edge length of 335.2 picometers. The beta form is rhombohedral. The structure of polonium has been characterized by X-ray diffraction and electron diffraction. 210 Po has the ability to become airborne with ease. If a sample is heated in air to 55 degrees Celsius, 50% of it is vaporized in 45 hours to form diatomic Po2 molecules. Even though the melting point of polonium is 254 degrees Celsius and its boiling point is 962 degrees Celsius. More than one hypothesis exists for how polonium does this. One suggestion is that small clusters of polonium atoms are spalled off by the alpha decay. Chemistry. The chemistry of polonium is similar to that of tellurium and bismuth. Polonium dissolves readily in dilute acids, but is only slightly soluble in alkalis. Polonium solutions are first colored in pink by the Po2+ ions, but then rapidly become yellow because alpha radiation from polonium ionizes the solvent and converts Po2+ into Po4+. This process is accompanied by bubbling and emission of heat and light by glassware due to the absorbed alpha particles. As a result, polonium solutions are volatile and will evaporate within days unless sealed. Compounds. Polonium has no common compounds, and almost all of its compounds are synthetically created. More than 50 of those are known. The most stable class of polonium compounds are polonides, which it prepared by direct reaction of two elements. Na2Po has the antifluorite structure. The polonides of California, Bar, Hg, Pb and lanthanides form a NaCl lattice. BePo and CdPo have the wurtzite and MgPo the nickel arsenide structure. Most polonides decompose upon heating to about 600 degrees Celsius, except for HgPo that decomposes at 300 degrees Celsius, and the lanthanide polonides, which do not decompose but melt at temperatures above 1000 degrees Celsius. For example, PrPo melts at 1250 degrees Celsius and TmPo at 2200 degrees Celsius. PbPo is one of the very few naturally occurring polonium compounds, as polonium alpha decays to form lead. Polonium hydride is a volatile liquid at room temperature prone to dissociation. The two oxides Pu2 and Pu3 are the products of oxidation of polonium. Halides of the structure of POX2, POX4 and POX6 are known. They are soluble in the corresponding hydrogen halides, i.e., POClX in hydrogen chloride, POBrX in HBr and POI4 in high. Polonium dihalides are formed by direct reaction of the elements or by reduction of POCl4 with SO2 and with POBr4 with H2S at room temperature. Tetrahalides can be obtained by reacting polonium dioxide with hydrogen chloride, HBr or high. Other polonium compounds include acetate, bromate, carbonate, citrate, chromate, cyanide, formate, hydroxide, nitrate, selenate, monosulfide, sulfate and disulfate. History. Also tentatively called radium F, polonium was discovered by Marie and Pierre Curie in 1898, and was named after Marie Curie's native land of Poland. Poland at the time was under Russian, German, and Austro-Hungarian partition, and did not exist as an independent country. It was Curie's hope that naming the element after her native land would publicize its lack of independence. Polonium may be the first element named to highlight a political controversy. This element was the first one discovered by the Curies while they were investigating the cause of pitchblende radioactivity. Pitchblende, after removal of the radioactive elements uranium and thorium, was more radioactive than the uranium and thorium combined. This spurred the Curies to search for additional radioactive elements. They first separated out polonium from pitchblende in July 1898, and 5 months later, also isolated radium. In the United States, polonium was produced as part of the Manhattan Project Dayton Project during World War II. It was a critical part of the implosion-type nuclear weapon design used in the Fat Man bomb on Nagasaki in 1945. Polonium and beryllium were the key ingredients of the Urchin detonator at the center of the bomb's spherical plutonium pit. The Urchin ignited the nuclear chain reaction at the moment of prompt criticality to ensure the bomb did not fizzle. Much of the basic physics of polonium was classified until after the war. The fact that it was used as an initiator was classified until the 1960s. The Atomic Energy Commission and the Manhattan Project funded human experiments using polonium on 5 people at the University of Rochester between 1943 and 1947. The people were administered between 9 and 22 microcuries of polonium to study its excretion, detection, gamma counting by means of radiometric methods such as gamma spectroscopy. It is possible to measure the concentrations of radioisotopes and to distinguish one from another. In practice, background noise would be present and depending on the detector, the line width would be larger, which would make it harder to identify and measure the isotope. In biological, medical work it is common to use the natural 40K present in all tissues, body fluids as a check of the equipment and as an internal standard. Alpha counting. The best way to test for many alpha emitters is to use alpha particle spectroscopy. It is common to place a drop of the test solution on a metal disc which is then dried out to give a uniform coating on the disc. This is then used as the test sample. If the thickness of the layer formed on the disk is too thick, then the lines of the spectrum are broadened. This is because some of the energy of the alpha particles is lost during their movement through the layer of active material. An alternative method is to use internal liquid scintillation, where the sample is mixed with a scintillation cocktail. When the light emitted is then counted, some machines will record the amount of light energy per radioactive decay event. Due to the imperfections of the liquid scintillation method and the fact that random quenching can reduce the number of photons generated per radioactive decay, it is possible to get a broadening of the alpha spectra obtained through liquid scintillation. It is likely that these liquid scintillation spectra will be subject to a Gaussian broadening rather than the distortion exhibited when the layer of active material on a disk is too thick. A third energy dispersive method for counting alpha particles is to use a semiconductor detector. From left to right, the peaks are due to 209 Po, 210 Po, 239 Po and 241 Am. The fact that isotopes such as 239 Po and 241 Am have more than one alpha line indicates that the nucleus has the ability to be in different discrete energy levels. Occurrence and production. Polonium is a very rare element in nature because of the short half-life of all its isotopes. 210 Po, 214 Po, and 218 Po appear in the decay chain of 238 U. Thus polonium can be found in uranium ores at about 0.1 mg per metric ton, which is approximately 0.2% of the abundance of radium. The amounts in the Earth's crust are not harmful. Polonium has been found in tobacco smoke from tobacco leaves grown with phosphate fertilizers. Because it is present in such small concentrations, isolation of polonium from natural sources is a very tedious process. The largest batch of the element ever extracted, performed in the first half of the 20th century, contained only 40 Ci of polonium-210 and was obtained by processing 37 tons of residues from radium production. Polonium is now obtained by irradiating bismuth with high-energy neutrons or protons. Neutron capture synthesis by reaction. In 1934, an experiment showed that when natural 209 Bi is bombarded with neutrons, 210 Bi is created, which then decays to 210 Po via beta- decay. The final purification is done pyrochemically followed by liquid-liquid extraction techniques. Polonium may now be made in milligram amounts in this procedure, which uses high neutron fluxes found in nuclear reactors. Only about 100 grams are produced each year, practically all of it in Russia, making polonium exceedingly rare. This process can cause problems in lead-bismuth-based liquid metal-cooled nuclear reactors such as those used in the Soviet Navy's K-27. Measures must be taken in these reactors to deal with the unwanted possibility of 210 Po being released from the coolant. Proton capture synthesis by N reactions. It has been found that the longer-lived isotopes of polonium can be formed by proton bombardment of bismuth using a cyclotron. Other more neutron-rich isotopes can be formed by the irradiation of platinum with carbon nuclei. Applications. Polonium-based sources of alpha particles were produced in the former Soviet Union. Such sources were applied for measuring the thickness of industrial coatings via attenuation of alpha radiation. Because of intense alpha radiation, a 1 gram sample of 210 Po will spontaneously heat up to above 500 degrees Celsius, generating about 140 watts of power. Therefore, 210 Po is used as an atomic heat source to power radioisotope thermoelectric generators via thermoelectric materials. For instance, 210 Po heat sources were used in the Lunokhod-1 and Lunokhod-2 moon rovers to keep their internal components warm during the lunar nights, as well as the Cosmos 84 and 90 satellites. The alpha particles emitted by polonium can be converted to neutrons using beryllium oxide, at a rate of 93 neutrons per million alpha particles. Thus BO-BeO mixtures or alloys are used as a neutron source, for example in a neutron trigger or initiator for nuclear weapons and for inspections of oil wells. About 1,500 sources of this type, with an individual activity of 1,850 Ci, have been used annually in the Soviet Union. Polonium was also part of brushes or more complex tools that eliminate static charges in photographic plates, textile mills, paper rolls, sheet plastics, and on substrates prior to the application of coatings. Alpha particles emitted by polonium ionize air molecules that neutralize charges on the nearby surfaces. polonium needs to be replaced in these devices nearly every year because of its short half-life. It is also highly radioactive and therefore has been mostly replaced by less dangerous beta particle sources. Tobacco smoke from cigarettes contains a small amount of polonium isotope 210, which can become deposited inside smokers' airways and deliver radiation directly to surrounding cells. The lungs of smokers can be exposed to 4 times more polonium than those of non-smokers, and specific parts may get 100 times more radiation. One study estimated that someone smoking 1.5 packs a day receives the equivalent amount of radiation as someone having 300 chest X-rays a year.